Okay. Oh yeah, we were going to get into the Van Deemter equation, weren't we?
Yeah. Then that was the last words I heard coming out of that class.
You always remember Van Deemter. Well, Lucian chromatography, that's kind of how we do it with an instrument, and when we're not doing column chromatography, or not column chromatography, but I'm not sure what you call that.
It's like the column you separate stuff.
Yeah. Well, we have columns here. There's a column. So anyway, this is the instrumental method of doing it. And we get things that look like this, right? Each peak is, I think the 5.596 is actually glucose. And 6.242 is like fructose or something like that. And the one at 8 is sucrose, combination of the two. Okay, and so we're going to start talking about theory, how all this works. And there's some different ways, a couple different ways that we kind of talk about chromatography and how it actually works. One is the plate theory. And you can see my plates. This blue column in the middle row, but if you put, but it's my column. And you can picture in any column these slices. And in each slice is where an extraction occurs. And it moves on into a new slice, and extraction occurs, moves on, and that keeps going on, and slowly a peak will move down a column. It'll spread out in those slices as it goes, but it'll move faster. Right? It moves faster down the column than it spreads. So this theory, and that's basically it. And it basically is kind of like, I'm not sure if you did fractional distillation, where you did a distillation and you have a tube with little glass beads.
I think maybe once.
Yeah, and it's a better distillation process because you have the solvent, the things that evaporate get pulled up into the glass and they recondense, but then they re-evaporate, recondense, and you get this process going up, and you get a better separation off the top. And it's kind of, it takes some of the ideas from that. And so this theory describes how the solute moves down the column, and it kind of helps us describe why we get Gaussian distributions, like our Craig countercurrent distribution thing we looked at before. But it doesn't really tell us why. We know it's kind of a random process, but it doesn't tell us why. Now, each of these plates, or slices, if you will, the slice right here, has a height equivalent of a theoretical plate.
What's the
It's something we can actually calculate. You might get it in millimeters or centimeters. And that's what, and if your column is 10 centimeters long and you have 1,000 of these, then each one is 10 divided by 1,000, right? And that would be the thickness of one of these plates or slices. So H is going to, when we write the symbol H, capital H, that is a height equivalent of a theoretical plate. It's the width of one. So if we know what the height equivalent of the theoretical plate is, and we know how long our column is, we can calculate how many plates we have. And a number of plates, if you have more plates, you end up with better resolution, narrower peaks, everything's better. You get a better, more efficient separation, call it. There's another term that we use for H, and we sometimes call it column dispersivity. the spreading,
Mhm.
how much spreading occurs. The smaller the H is, the less dispersion occurs as a solute moves down a column. That's why we call it column dispersivity. Now you can actually calculate these in real life. If you know the length of the column, H is going to be equal to the length of the column divided by the number of plates. But we can actually determine experimentally, this is the length of the column, and the sigma squared is the standard, well, sigma equals the standard deviation of this Gaussian. It's the width at, I think it's 3/5 height. It's the width or spreading. So standard deviation is how spread out your data is, right? The smaller it is, the better. Well, you can just take that and square it, and that's something called the variance. And the variance, well, you really don't really need to know that. You just square it. So you have a peak that comes off a column. You measure this, you measure sigma, you square it, then you divide by the length of the column, and you get what 1H is. Or you can take that H and multiply by, well, take length of the column, divide by H, and that gives you the number of plates. So you can calculate back and forth between these. So it's actually a experimentally determined value. Does it really mean much? Because there aren't these little individual plates. Things are more continuous than that. It's not digitized. So anyway, this is plate theory, and it introduces us to this idea of these little slices or plates, and the greater the number of plates, the smaller the column dispersivity is, the narrower the peaks are, and the narrower they are, the better resolution you're going to get. You're going to be able to separate your peaks better. So that's what we mean by separation efficiency, being able to separate all the peaks. Okay, there's another theory called the rate theory. We're going to use some of the same terminology, but it does a better job not only of describing the solute migration, but how bands broaden. And it kind of describes why, to some extent, it can help to describe why peaks travel at different speeds and things like that. But it describes the how, and why. Okay. And this is a picture that describes it right here. You have mobile phase coming from the right? And so we have this column that looks maybe like this, and mobile phase is moving from left to right. And we say, what we're saying is maybe you have one little solute molecule right here, this little green dot. And as it moves along, it's going to be pushed from left to right, but it will diffuse a little bit. It moves randomly a little bit. And so it could, on occasion, move against the flow of the mobile phase. And what that means is it'll slow down a bit. And so it can move along, in this direction as well, up or down, sideways. And so it can move down through the column. And it's going to take some random path as it gets pushed along, but it can get behind particles. Most columns are filled with particles, and the particles hold the stationary phase. So this particle, this molecule, analyte molecule, solute molecule, moves along. It can get behind one of these particles, and when it does, it slows down. And it can move around a little bit randomly until it gets into the flow, the flow of the move phase. Yeah, it's like the rocks in a river. You get a little eddy behind the rock. And by the way, when it's back behind these particles, it's called eddy diffusion. And now occasionally it'll bump into the stationary phase and it'll get absorbed into the stationary phase right here.
Is that adsorb or absorb? I think it's adsorb.
It can be either.
Oh, really?
But I'm going to call it absorb. When you look at these particles, they're usually made of some somewhat spherical solid. This is a solid, but on the surface of that will be some liquid type material.
Mm-hmm.
And so your solute particle can kind of move to the surface, and it can equilibrate or extract into that. And then once it gets into here, it can move around randomly until it reaches the surface again, and then it comes out.
Okay, so this particle, what is it? Just a particle we're trying to measure?
It's the solute molecule.
Okay, cool.
Solute molecule. Yeah, it'll usually be a molecule. And when it gets into the stationary phase, that's when retention occurs. Mm-hmm. The longer it stays in the stationary phase, the longer it takes to form, right? And that's where the partition coefficient becomes important. So, and then it pops out, it randomly moves around, it bumps into another one.
It goes through it, comes back down.
Yeah. So notice this particle followed that green path I drew.
Mm-hmm.
That's its path. But if you took that exact same particle and put it in the exact same place with exactly the same conditions, will it follow exactly that same path? Nope. It has almost an infinite, well, not infinite, but a pretty close number of ways it can move down through the column. And some of those paths are going to take longer than others.
Yeah, it might like pop out in a different spot.
Yeah, or it might stay in the stationary phase a little longer. Well, on average, one set of particles will probably, on average, stay about the same amount of time in the stationary phase. And that's what gives you the retention time. Mm-hmm. But some of them are going to move around differently. Some will move more quickly, will spend less time in the retention in the stationary phase, some will spend more time. But some will spend more time in the eddies, and some will spend less time. And that's what causes the spreading of the peaks, right? And we get a Gaussian distribution. Some are moving more quickly, some are moving more slowly. But on average, they're taking about, on average, the same amount of time, right? Mm-hmm. And that's, so some particles during migration undergo many transfers with a stationary phase. Variability in the resonance time for a solute gives band shape. That probably has more effect than getting in the eddy, though. That's probably true. The resonance time in the stationary phase is more important than being in an eddy in this area or this area. It's still going to move along fairly quickly. A little bit of spreading because of that, mm-hmm. but not much. And the variability in resonance time by two different solutes explain their movements down the column at different rates. If you basically understood this diagram and what it's trying to show, that's most of chromatography.
We'll get an A on the next test.
Maybe so. At least on those questions.
Yeah.
I mean, different solutes have different partition coefficients, so they'll spend more or less time in the stationary phase, so they come out at different places. They get different peaks, right? Different retention times. But they'll both kind of spread a little bit, and their spreading depends on how much time, well, differences in retention time in those different phases. Okay. That even happens when Laura isn't here.
What was it? Sorry.
When I accidentally move forward.
No.
Okay, so that's kind of important. Okay, the efficiency, I mentioned this idea of efficiency. How well does a column do the separation? And there's the equation basically. Yeah, the number of plates is equal to L times L over that, right? That'd be L over H. L times 1 over H. Yeah. Okay. Now the Van Deter equation. Let's see if we can get done with it today. Okay, here's the Van Deter equation. It has, this is, by the way, it's an empirical formula. I think what that means is you can't really do a calculation with it. Its purpose is more to show which variables affect what and how much, relatively how much.
Kind of like the parameters and stuff, you know,
Yeah.
switched around.
Yeah. And so you see there's 3 parts to this. There's this, what we call the A term, the B term, and the C term. And we're going to look at each of those terms and how different variables affect. And how different variables affect the column dispersivity, right? Or band spreading. Band spreading. So column dispersivity and band spreading are basically the same. Okay, first is the A term, and this is the eddy diffusion term. This is where trout want to be, right? They want to get behind the rocks where it's less movement of water, so it's a little less energy draining. And they can shoot out and get food whenever they get
Still water, shade.
Yeah, a depth. Fish look for depth for protection. They want protection, they want food, and a reserve of energy, right?
Mm.
So they'll usually sit on the edge of current because food's coming by in the current, but they'll try to stay out of the current directly if at all possible. But they want some water that's deep or that's agitated so birds and things can't see them. Well, anyway, this A term is usually small and not well defined.
So it's kind of like a educated guess.
Yeah, well, it's just, you know, the particles. Here's the particle and it's moving along and it gets behind and it spends some time around here, then it gets out and moves along, gets behind another particle, and then it gets out, you know. And it's really not as important as the other 2 terms, pretty small.
Mm-hmm.
It has some effect, but it's, and they really, it's just not well defined. So that's about all we can say about it. It probably is smaller with smaller particle sizes. I would say it decreases with smaller particle sizes. Right. But if you have big particles packed together, or if you have little tiny ones, well, there's less eddy with those small ones, right? You're sort of, if you go to the limit, which means 0 particle size, then there's no eddy diffusion.
Mm. Well, it'll just be mobile phase on mobile phase then.
Yeah. And that's what gas chromatography, what happens with it. It doesn't have any diffusion. There's no particles.
Mm-hmm.
Okay, the B term is a little more interesting. And notice the effect. This U, by the way, this is flow rate. That's how fast the mobile phase is moving. And notice this in every one of these terms. Now, actually, it's really not the flow rate, it's the linear flow velocity. It's how much flows, how many centimeters it moves per second, per minute, whatever. But flow rate's close enough. And you notice that you increase the flow rate and it makes this term larger, which means H becomes larger.
It makes sense.
Yeah.
It makes sense.
Yeah. Now you notice with the B term, if you increase the flow rate, it actually makes it H less.
What is the
We
longitude?
haven't got to B yet.
Okay.
And if you go to the C, when you increase the flow rate, it makes H become larger. So B and C are competing with each other in terms of flow rate, and C does a little bit with B as well, but it's not as big, so it's not as important. So we're going to look at each of these. Oh boy, that's way too fast.
Understood it all.
The B term is called the longitudinal diffusion. And if you just have an open column, if you just have an open column with no particles, what's going to happen is if you have a slug, a sample, over time it's going to spread out, isn't it? It's going to diffuse along the axis of the column, or with the axis of the column. So there's just going to be this general spreading by diffusion. And that's basically what this is about. You notice in these in the B term right here, you have a D, well, that's the diffusion coefficient. D sub M, well, D is the diffusion coefficient. Which is basically how fast something, well, how fast it spreads out, it diffuses.
So say again. So what is diffusing? What is that little middle piece in that drawing?
Which one?
In the drawing?
Oh, I mean this right here?
The middle piece.
This right here? Oh, this right here? Or I'm not sure what you're talking about.
The little drawing up here?
Oh,
What's the little middle piece? It's like the filter? Or?
I mean, if you inject a sample,
Mhm.
you inject it as a slug.
That's,
A slug, a little rectangular
okay.
concentration. It had this area, this volume here contains your solute.
Okay.
But over time, it's going to spread out, isn't it?
Mm-hmm.
It's going to spread out. So a little bit it's going to diffuse this way, a little bit's going to diffuse this way. I mean, just like if you put a drop of food coloring in water, they'll just spread out.
Or like directions. A tea bag.
Yeah,
you know.
Exactly.
Okay.
It just spreads out. And that's what's going to happen with any injection of a sample
Okay.
into a column.
I got you now.
Okay. That's wondering where you're going with that.
I didn't know what you said slug. I was like, I don't know.
It is kind of a slug. It's not a bug slug.
No, I realized that, but I didn't know what the other slug meant. So
yeah, an injection. How's that?
Okay, I like that.
Sample. Okay, so these D's are diffusion coefficients. This is the diffusion coefficient in the mobile phase. And this gamma is what's called an obstruction factor, and it depends on the size and shape of the stationary phase particles. Stationary phase. Particles. There's something about my pad here that. And so, the larger the diffusion coefficient, you can increase the diffusion coefficient by increasing the temperature. Things will spread faster. Yeah, more kinetic energy, more mobility. So this is pretty typical for liquid chromatography, but for gas chromatography, it's different, right? Here's for gas, what we find is diffusion coefficients of a gas are going to be a lot bigger than diffusion coefficients of a liquid. And so this becomes a little more important. So in a gas phase, things can spread out faster. So GC, this will be a more important term. Diffusion increases with time. Well, yeah, diffusion and spreading increases with time. The rate of diffusion stays the same, right? Unless we increase the temperature, then it speeds up. Okay, and that makes sense. You think about B in the mobile phase, the less time it's on the column, the less spread out on B. You know, your molecules are spreading out with time, but if you push it off the column real quick, it won't spread much.
Yeah, that makes sense.
So as the flow rate becomes larger, there we go. The flow rate becomes larger, that it doesn't spread as much. It doesn't have a chance to spread. Yeah. That was a fairly uncomplicated one, I think. Mass transfer is a little more complicated. The mass transfer term is often written as two terms. It's the mass transfer in the stationary phase plus the mass transfer in the mobile phase times the flow rate. And so there's two terms that we need to talk about because, you know, solute is moving around in the mobile phase. And mass transfer means basically it's all about the transfer between the mobile phase and the stationary phase. There's that equilibrium between two. How fast does it get to the mobile to stationary phase and gets absorbed? How fast can it get back to the surface and get out? And move down the column. You want this process to be fast. One of the things we do is sometimes we increase the temperature to get this to happen more quickly so that we have equilibrium. Because if you push things down the column too fast, they can't reach equilibrium. So by heating things up, we can get things to, we can keep our Gaussian peaks. Here's the mass transfer in the stationary phase.
Well, okay, this got way more complicated all of a sudden. This went from just CU to Q times Q prime.
Okay. Well, let's look at what these things are. Q is a shape factor. It's not something you can adjust or do much with. You buy a column, and most of those columns, they try to make sure the stationary phase particles are pretty spherical.
Yeah.
So it's probably pretty constant for most. Now, yeah, K prime is something called the capacity factor that we'll talk about. It's related to the retention time, and that's kind of related to how long it's on the column. If it has a long retention time, then it's been there a long time on the column a long time. D sub F is the film thickness, because remember the stationary phase is a spherically shaped particle with a liquid on the surface. This is solid. Draw my dash is very good. And you know, how thick is this? If it's really thick, a solute particle could get into it and stay there a long time. If it's thin, it can get in and out quickly. And there's advantages to either of those.
Yeah. I bet they play off each other. Yeah. Happy medium kind of thing.
Sometimes you can buy columns with thicker stationary phases, thinner stationary phases.
I guess it all depends on what you're doing too.
Yeah. What group of compounds you're trying to separate. If they don't separate very well, you might want to go to a thicker stationary phase and cause the retentions to be longer. And so that things have more chance to separate. Diffusion coefficient in the stationary phase is there as well, right? And this is where if we increase the temperature, that diffusion coefficient increases and C sub S becomes smaller. So this is where temperature can be helpful. It doesn't help with the B term. Increasing the temperature means they spread out faster. That's not good. But here it'll help get things back to the surface of the stationary phase quicker. K prime. It's some function of how long the solute particle stays on the column, related to retention time. Here's the mass transfer in the mobile phase. This is even more complicated because notice it just as a function of those three terms. That's dependent on particle size, column diameter, and flow rate. Remember, particle size is not the thickness of the stationary phase, but it would be this size, right? And yeah, that makes sense. Oh yeah, if we want this to be smaller,
We want it to be.
yeah, because if it's smaller, that means this is smaller, which means H is smaller. The column dispersivity is smaller. We want the column diameter to be narrower, right? Here's our column, and it's packed with little particles, but it has a certain width to it, right? Diameter to it.
Okay, so we
want it small. Everything smaller is better.
so even CS.
Yeah, oh yeah, because remember, H is equal to the A term plus the B term plus the C term. The smaller C is, smaller H will be.
And we want a smaller H.
And the smaller these are, and even the flow rate. Now we want the solute particles to be moving fast, diffusing fast. And that'll make H smaller. But there's always this kind of competition between that B and C particularly, with flow rate and with temperature. You just do what you need to do to get a good efficient separation. Okay, column size. There's actually, for the longest time, HPLC columns were about a 1/2 centimeter in diameter. I think 4.6 millimeters, 1/2 centimeter diameter. But they're making columns that are like a millimeter.
It's crazy. I mean, just
and they give better separations. But you need more pressure to push stuff through that narrow opening. And you need really fine particles to put in that.
yeah, it has to be like pristine.
Yeah, everything has to be smaller. Yeah, like for everything. And they can do really good separations much quicker.
Well, because they're smaller, I would say,
Yeah,
and the pressure you're having.
Yeah, everything's helping make sure we get less broadening because it's on the column less time.
Increase the temperature.
Yeah, do all kinds of things. Okay, so that's the Van Diepter equation and all those terms. Just a little more about mass transfer. Here's a column. Flow rate's going this way, and this is in a column. And you can see this, maybe this is kind of the surface. And as a solute moves through the column, some of it's dissolved in the mobile phase, and some of it has been dissolved into the stationary phase. And as this moves along, this will move forward, right? And it'll start equilibrating here with a new stationary phase, right in here, which means this has to re-equilibrate with the mobile phase a little bit over here has to re-equilibrate with the mobile phase. And so there's kind of this little spiral that goes, as it moves down the column. It has to equilibrate with new, and then it has new stationary phase. It has to equilibrate with new mobile phase as it moves through. Now, if the mobile phase is moving too quickly, pushing this through too quickly, this is what's happening here. What happens is this moves too fast, and we don't get equilibration. Things don't have enough time to equilibrate here at the beginning and the end of this peak.
Do we want equilibration?
Oh yeah, the equilibration gives us a nice Gaussian. It gives us a linear isotherm. Remember isotherms?
Yes.
You remember the term?
Yeah. Isotherms, well, it's just temperature dependent.
I'll tell you what, a linear isotherm. Here is an isotherm between the mobile and stationary phase.
Okay.
And we want a constant concentration in the stationary phase and mobile phase as it moves through the column. And if that happens, then everything is just determined by random processes, which gives us a Gaussian distribution, Gaussian shaped peak. And we like Gaussian shaped peaks.
Yeah, you do.
Usually, well, when things absorb into a liquid stationary phase, things are faster. If you're doing adsorption, things are pretty quick usually. But if you're doing absorption,
Well, it takes time because it's going in.
yeah, exactly. It's slower. It's slower in a liquid stationary phase, and so their flow rate becomes more important. But even with adsorption, there could be issues there as well. And so at too large a flow rate, you get non-equilibrium. Okay. Now, trying to think if there's another slide coming up that talks about isotherms. I thought there was. Yes, there is. We'll get to it at some point. But this is actually called a Van Deemter plot.
So just H over time.
Yeah, you plot the column dispersivity or the plate height versus the flow rate. And you can determine this experimentally. That'd be a good idea.
My bad. You used flow rate. I said time.
Yeah, oh yeah. It's related to that. But what you find is that at slow flow rates in this region right here, that H becomes large. Things are on the column too long, and they have plenty of time to spread out at slow flow rates. So the B term becomes very important.
Yes.
But at fast flow rates, it becomes bad as well in this region. Because you're moving along too fast, you don't have equilibrium. Things don't have a chance. The mass transfer between in the stationary phase and mobile phase don't move fast enough to keep up with it. And so what you find is you have an optimum enthalpy, column dispersivity, at a certain range of flow rates. Now in HPLC, in liquid chromatography, that's somewhere between 0.5 to 2 milliliters per minute. Where's my pen? You get rid of that. It's usually in that range. We run separations at about 1 milliliter per minute. And those 4.6 millimeter columns that are typically used. In gas chromatography, this might be more like 30 milliliters of gas per minute. But there'll be the optimum range where we're going to have things we're going to get a good small column dispersivity, so peaks will be narrow, but they'll come off in a reasonable amount of time. All right. Now a little bit more about mass transfer. We want to use thin films. that decreases the film thickness. When the film thickness decreases, that decreases age.
Mhm.
Usually, I guess I shouldn't. This is really increasing high temperatures increases the diffusion coefficient and makes sure mass transfer is reached more easily. You can use higher flow rates with higher temperature, but there's a limit. This is limited. You get too high a temperature and you get too much spreading.
It goes too fast.
The
to
B
capture.
term becomes
Yeah.
too important. Let's see what else. Oh, smaller particle sizes. I'm kind of, this is just a summary of all the ways we can improve separations. Decreasing this will decrease age. This will usually decrease, to make our separation better, or shapes, peak shapes are better, more Gaussian. We want to use smaller column diameters, that decreases age. And that's it. The main things that we can change. You can buy a new column. Basically, that's how you change most of these things. The ones, the first one and the third and the fourth, film thickness, particle size, and column diameter are all changed by picking a new column.
There's something in lab. I don't know what it's used for. I've only seen it very rarely, but it's like a column with beads in it. And is that like what we're talking about?
Well, that'd be column chromatography. That'd be more.
I don't know what it's used for.
It could be ion exchange.
Oh yeah.
What you do is you pass. There are columns with these beads, polymer beads that have sulfonic acid groups on them, and you can pass acid through, lots of acid, and that'll just protonate all those acidic groups. And then you come along with something like lead, a sample that has lead in it. You pass it through, the lead will find, well, you rinse the column out of that acid, so you only have a column polymer with the acid groups. Then you pass lead through, and a lead ion with +2 charge will kick a proton off and stick to it.
Okay.
And you can use that to concentrate lead ions. And then you could come along later and you can eject the lead with acid again.
It's just back and forth.
And then you can collect the lead, and you got rid of all the impurities, things that could interfere. And
you just have pure lead now.
There's actual liquid chromatography like this that uses ion exchange as well. It's columns with positive charges or negative charges, but they use certain buffers to kind of affect how much something wants to be retained by these charge groups. Then you can separate them. Okay, so those are the things that cause broadband. That's why bands broaden and move down columns. There are some other things that we might consider. There's some other things that can cause the spreading of peaks other than the column itself. And the column, this is the band spreading by the column. If you have three, if you're adding three things together that are independent of each other, well, if you're adding, think about column propagation of uncertainty. Remember that? That's the uncertainty or the error of some value, some result is equal to the error squared. Like if you're adding two numbers together that have uncertainties or standard deviations, you can take the square root. Well, the variances of these two independent things add together gives you the variance of the result.
So just add those together and you get the.
Yeah. So these are independent. The spreading that occurs, the spreading is like standard deviation of the column is one thing that spreads our peak. But there's The injector itself, when you inject the sample, there's a little bit of spreading that occurs there. And there's some tubing. It goes from here to here, right? Tubing. And so as it moves through this little bit of tubing, you get to the column.
It might get caught in too.
Well, there's going to be a little bit of dispersion.
Mhm.
And after the column, it has to go to the detector. And so there's some tubing there, but also the detector is some chamber with lights shining through it, and it goes in and it gets a little bit diluted and spreads out a little bit in the detector.
So you don't want the machine to be too long or too short.
Yeah, we want this tubing to be short. We want the detector and the injector to have as little spreading as possible. But these are some things that can cause some spreading that you wouldn't predict. Okay. Just want to let you all know about that. Oh yeah, we have a little bit of time. Nonlinear isotherms. That's what I was talking about when we want linear isotherms. What we find is that equilibrium, the partition coefficient K is not always constant with the concentration of solute, especially in a liquid stationary phase. So what we find is that linear isotherms do give Gaussian distributions, and that's why we want the kinetics, if you will, or the mass transfer to be fast so that we can make sure we reach equilibrium. And so we can have this linear isotherm, which will give us a Gaussian shaped peak. Nonlinear isotherms give tailing or overloading. These are two things that can happen. Let's see if here's a picture what it might look like. You know, a linear isotherm would be linear the whole, be linear up through here, right? And that means that the properties of the solute in the stationary phase is the same, or mobile phase is the same as the properties of the solute with the mobile phase or stationary phase. They're the same. And so the solubility in K doesn't change if this is linear. But what we find is sometimes you have overloading, for instance. So maybe normally it would look like this, it'd just be straight. But as your concentration increases in the stationary phase, it doesn't want to dissolve anymore.
Not like it's getting, a traffic jam,
There's a maximum absorbed. Solubility has been reached, basically. Or at least the properties are changing, less soluble. New stuff cannot dissolve.
So I guess when that happens, the rest of the stuff you're overloading it with will just pass through, wouldn't it?
It goes through without being absorbed and being retained. And so peaks will often look like this.
But this one just keeps going straight up because the
See, this is the fronting. If I could just write fronting without having a mess.
it's cursive.
Fronting. And so this is the front of the peak. This is what's coming off first. It's just blowing through, whereas some of it's being retained. And it's an ugly peak. You see this in GC all the time. If you inject too much sample, it can't all interact with the stationary phase, so it just flows through very quickly. Tailing is a little bit different. There, the peak will look kind of the opposite. It'll be Gaussian, but then the end of it will have a long tail that drags out. And so here's a tail. And there what's happening is there might be on the stationary phase, here's our stationary phase, and you have this liquid, but there might be parts of it that don't have a liquid on it. And you might have, this is usually silicon oxide, by the way. Silicon dioxide. And so this has a little bit of a polar, and this might be non-polar. But this would be polar. And so a solute particle might actually adsorb here more slowly
Mhm.
and hang on and not come off as quickly. And so you get this tailing.
So just some things are dragging,
Yeah,
basically.
yeah, you're dragging those behind.
Mhm.
So that's something that can happen that you might see. So in GC, we have a really hard time. We need to make sure that we inject a sample, that we only inject a very little bit
Mhm.
so that we get nice, good peaks out of it. HPLC, it can happen in HPLC, but there's a lot more stationary phase. So it's not quite as much of a problem. We get more tailing
Mhm.
in LC. This is LC is more likely here than GC. More likely for this, but it could happen in either. And I think that's probably where we can stop.
All
And that's
Just a few more slides to go. We're done.
oh boy.
Then I guess it's test time after that.
Oh, we'll just wait for the final. Yeah, there's actually more than you think left, but hopefully we can get it done, and then we can go on to GC and HPLC so you can see how all that works.
That's Tuesday.
Yeah, well, you're going to take an exam Monday, right? Both of you are going to take the exam Monday, and we'll finish up this on Monday, this chapter, and then on Wednesday and Thursday, and probably Monday, we'll do GC, and then the next Monday and in the next week we'll do liquid chromatography, and then we'll maybe have some free time towards the end.
Okay.
We'll see. Let me turn this off. I can get my mouse. I need to stop recording.